Okay, we're going to understand Green's theorem if it kills all of us. Okay. And it starts with this block. Now we can see that this wood block is cut off down here so that the sides are perpendicular to the plane this thing rests on. We can also see that we've got some slope here, okay? And we've got some slope in this direction. This is going to represent a section of the graph of a function. So right now, function's coming out of the board at you. So your function values are in the z direction. And your function is, I think it's going to be a rough representation because of the chalk thickness, but that's okay. Okay, so we have this rectangle down in the XY plane. So we got an X and a Y axis. Doesn't matter where the origin is. Origin could be anywhere. We're not particularly interested in that. But what we are interested in is the integral over this part of the boundary and the line integral over C1 of this function. Okay. So we're interested in the integral over C1 of f of xy dx. And the question I've posed is, what do you have to measure? Okay. So we take a measuring instrument, which I don't have. Let me borrow the. We can demonstrate how we measure things, and we know, of course, but just make it really concrete. We can measure this distance. Okay. That's going to give us a delta x, right? And we can measure other things. But right now, we just measure that. And when I measure this, I get 8.9 centimeters. So we measure that. Now we label that. Now, everybody pretty much started just by measuring that. Okay. So that's very good. We can say then that here, your delta x is 8.9 centimeters. Okay, and that would be compared to here. And I wrote that carelessly. Could have made that a little clearer. Okay. So we got delta x equals 8.9 centimeters. So we can approximate this interval. Find f of x, y, delta x. Okay. Now we've had, in some cases, a little trouble figuring out what we would use for the value of f of x, y. Well, if this thing's sitting here, the values of f of x, y, this surface here is taken to be part of the graph of f of x, y. Okay, so when we put this down here, we got the graph of f of x, y floating above the xy plane. And our values of f of x, y at any point are what we get if we measure the distance to this plane, and the stupid camera's out of focus. It's a great camera, but I don't know why it wants to go out of focus. Probably because it just doesn't really want to focus on me. Okay. And who can blame it? It still looks blurry to me. I'll pause this screen for a second. See if I get the camera to focus. Okay, it seems the only way I can get this to focus is to hang the picture a student a few years ago drew for me of the fact that log to the base 2 of anthill equals aardvark. Okay, which is relevant to the way I often talk about logarithmic and exponential form. It would be 2 to the aardvark equals anthill. But we do that in symbols too. Okay, well, that's not totally relevant, but at least it focused the camera. So let's focus our attention again. Okay, so again, you need a value of f of x, y. It could be an average value, but we're going to be content with any value right now. What are the values of f of x, y? Well, you take a point x, y. The value of f of x, y is how far you got to go here to get to the surface. Also, you have to be below the surface, it's negative. We're going to assume everything's positive right now. Okay, so we've got this dimension. What do we do next? Again, there was, in some cases, some hesitation here. Okay, well, the value of f of x at this xy point, which is down on the plane, is this distance. Okay, so it would be sufficient to measure any old distance just to get a rough estimate. You're not going to be too far off because the value of f of x here and here, where f of x is maximized here and minimized here on this surface, on this rectangle, okay, above this rectangle, they don't differ by even 10%. So you got to be accurate to within plus or minus 10%. I'd say plus or minus 6%. And you measure, see how close I am with that. Okay, if we measure any old point. So we measure any old point. So we could say, okay, at this point, which I'll call, I'm gonna have to draw a bigger picture of this so I can label things. This is in the large picture. Here's C1, I'll label it inside, although I don't like to do that. Here's C1. You got your delta x, which is 8.9 centimeters. And again, I need to label a point here, so I'm sure I'll label that somewhere else. Okay, so here's your point. We'll just take this as a point x, y. And f of x, y is what we get when we measure this distance. Okay, well, the way I've got this position, it looks like my y, my xy is maybe right here. Hopefully we can see this. Okay, so right there is my xy. I measure from here up to here. Try to draw a straight line. So this distance is f of x, y. Okay. Hopefully we can see this. And hopefully the camera will focus again like it did before. Okay. Well, let's just measure that. I'm getting 16.4 centimeters. So figure out that's what. Well, looks like we've got what we need to make an estimate. So this is 16.4 centimeters times 8.9 centimeters. Now I'll proceed to make a fool of myself by attempting to multiply that. Okay, 16 times 9 is 16 times 10 minus 16. 160 minus 16 is 144. If you don't happen to remember, 16 times 9 is 144. Okay. And this is like about 1% less than 9. It's 1 out of 89, which is pretty close to 1 out of 100. So let's just estimate that's 1% less, which would be about 1.4 less. So that gets us down to about 143. So then we got this 4/10 times 9, 3.6, gets us up to about 146. And of course, my arithmetic can be checked. It's probably wrong. Plus or minus 1, plus or minus a half. That's probably about right. Okay. So right there is our estimate of this interval. Now, if I'd chosen a different point, it would have gotten a different measurement for f of x. Okay. But on this, my minimum measurement is 16 point, or my maximum is 16.7. My minimum is 17.7. Okay, that's a difference of a centimeter out of about 20 centimeters. So my 6% estimate holds up real well. Now, those estimates and so forth aren't that relevant, but you want to make this as concrete as possible so you understand it as concretely as possible. If you have a formula for your function, of course, you can plug in the coordinates of any point and figure it out. Okay, then you need to know where the origin is, so you need to know what the actual coordinates of this point are, okay? And your delta x and so forth. Once you know the coordinates of this point, then you can do the whole thing with formulas, okay? Now, another thing that somebody did was, you know, one member of the class wanted to call this xi, y sub xi, y sub I, okay? I would say that we want to call this point, I can label it up here, so I will. Xi, y. Y is the same here as it is here, so we don't have to put subscripts on it, it's just some value. Over here. And this would be xi minus 1y. And this would be xi1, which then places this within a partition of some larger interval. Okay. And that's a very appropriate thing to do. So we can say that, okay, this is x. Okay, well, this is xi minus 1y, this is xiy. Then what would we call the coordinates of this point? Well, this would be, using the notation that we should be familiar with in partitioning intervals and so forth, that should be xi star y. Okay, not written very well. Chuck's being a little uncooperative and I'm being a little less aware of it. Okay, anyway, you get the xi star y here. So now we can say, well, okay, this is actually over the interval C1 could be written as f of xi star y times delta xi, when we know that delta xi is xi minus 1, this distance. We're familiar with that. I think we're okay with that idea. Okay, so this line interval is going to be approximated by this. And if this is a very small increment, instead of a big old chunk of wood, this represents a very small X increment. We don't expect f of xy to vary by much over here, between here and here. We've seen that it varies by about 6% in this case. But if we subdivide this into much smaller, toothpick size pieces to approximate this. Okay, like if we slice this into toothpicks and, slice and put them all together, and if our slices have 0 thickness, then we get a better approximation of what the integral from here to here is. But we would be focusing on this cell variable. We'd actually partition the path from here to here. And we have typical subintervals here and typical x of I stars. Okay. Well, okay. That's what kind of comes out of this exercise that I gave you. And we're still in the exercise, we're just getting started. But we see that now that we have a notation that we're familiar with that represents the approximate integral from here to here. Okay. Next thing I want is, with good measurements, do the approximate integral over C3 from here to here. Using the sample point, I'm going to call this, using the same xi star, but now we've got a different value of y. Well, we're going to call this y plus delta y. Now, I want you to figure out what the integral would be here, again, using the same sample point to estimate your f of xi star y. And you're also going to want to measure delta y. Okay? So let's see what happens. Okay, we did quite well here. Now with my estimates, let me just show you. Okay. Hopefully that's focused enough. Remember, we had 16.4 centimeters here. Now, I don't know what I did wrong when I measured it, but I got something quite a bit different, but we're going to go with 16.4 centimeters. Now we notice, if we look from the side, that this thing does have a slope. Okay, it's higher. It's higher here than it is here. And of course, here's your y plus delta y, here's your y, right? Y is one thing here, and you add a delta y, which is this, which at least one of you measured, maybe all of you. I don't, didn't look that close. Okay. And if you did, that was great, because it was exactly what you want to do. Okay, so a little more notation. What in the world is my sharpener? Yeah, figured somebody's trying to steal it. Yeah, I tried to steal your pen the other day, so that's we're even. And you do want to try to keep up with me on that. Okay, so this is now your f of xi star y. We want to go back here and measure f of xi star y plus delta y. Now I'll write this on the board in a minute, but we want to see what it is. Okay, and I'm getting 16.4 centimeters here, 16.9 centimeters here. And notice, keep myself honest, I drew a nice straight line perpendicular, hopefully, to the side here, so that I knew where to measure this. If I put my pen on this, we can see that there's a definitely a slope here. Okay, from here to here, a positive slope from this side to this side. Also, I measured the delta y. Since some of you did that, it's going to be relevant. Not yet, but it's going to be relevant, okay? That very soon it's going to be relevant. Okay, so I measured a delta Y here. So now I've got a few more measurements. First of all, my f of xi star y plus delta y is f of xi star y is 16.4 centimeters. F of xi star y plus delta y, in my case, is 16.9 centimeters. So my integral here is going to be approximately 16.9 centimeters multiplied by what? Well, multiplied by my delta x. The delta x from here to here. What is that? You might think 8.9 centimeters, and everybody kind of uses that. And that's not surprising, you know, you're focused on the notation and all kinds of stuff, but it's actually negative because you're in the negative direction. So it's negative 8.9 centimeters. Well, in calculating this, if you use a machine reader calculator, of course, you're not going to think about this, which is another reason I hate using machinery. We can do otherwise. Okay, well, 8.9 centimeters differs. No, sorry, 16.9 centimeters differs from 16.4 centimeters by half a centimeter, right? So the magnitude of this should be half a centimeter times 16.9 centimeters, right? Which would be 8. 146 centimeters squared, but negative plus 0.5 centimeters times 16.9 centimeters equals, I'm going to write this as negative 146 centimeters squared minus 8. Now it's 8.45. I'm going to round it to 8.5 centimeters because to use 8.45 would be too many significant figures for the accuracy of the measurements. But you could use 8.45 here if you really want to see what it is. Okay, so in my case, then, put a hard block back up here. He or she lives, they live all the way up there. Can't get used to using they as a single. Okay, eventually maybe. Okay, so centimeters squared down here. Writing it this way. This equals negative 8.5 centimeters squared. Now, the function's higher here than it is here. How did we end up with a negative? Okay, well, let's discuss that for a second. Okay, so we've got a good answer. It's because the integral over here is in the negative direction. Okay, your number is bigger. You know, your number is bigger by 8.5 centimeters squared. So you get about 155 centimeters squared as opposed to 146, right? But since you're going in the negative direction, the fact that it's bigger here makes your result for the two integrals negative. Very important point, and one that's a little confusing a lot of times. Okay, well now, what is your value of partial of f with respect to y? Just according to what you've measured. Okay, got a good answer. The partial f with respect to y. Now this is a slope. Okay, slope of a tangent line. Slope of what tangent line? Well, slope of the tangent line that we get here. Oops, out of the camera, okay? And right there is where we're measuring. There's our sample point. There's our sample point. From sample point to sample point, we've got some kind of a slope here, right? And you can see clearly this is an upward slope as we go in that direction. So we're going to approximate that. I'll just mention it's the slope of a tangent line. I'm not going to try to draw a picture since I already showed you. But and, you know, somebody said slope, somebody said, started to say change in before somebody else said slope. So you're both on track, and I think everybody is. So this is change in F over the change in Y, right? From here to here. Well, F changes from 16.4 centimeters to 16.9 centimeters. Over. What did I get from my delta Y? Write it down here. I did write it down here. What's our delta Y? Okay, now I remember, but the delta Y is about 3.5 centimeters in this case. And you have your own measurements. And that's approximately 5 over 3.517. So that's about 0.14. Okay. Okay, well, let's remember that because this is relevant to Green's theorem. Now you keep wanting to do double integrals so you have an idea what Green's theorem's about. Not necessarily quite getting the right things in there. We're going to have to see how that works. So we'll just kind of hold that for a minute, okay? That's going to be real relevant. Okay. Now, we've got another function, g of x, y. Okay. And we want to evaluate its interval over C2 and C4. Right? So what do you have to measure? Now we're going to have to, we're out of time. Hopefully, this is going to be a good exercise. And the goal is that you should then look back at the proof of Green's theorem and understand everything that you see. We have all the notation here for these two parts of the path. And we have two other parts of the path, C2 and C4, and some other function g of x, y on that path. So take your measurements and then work this out numerically. Then take a good look at Green's theorem. You also want to estimate the location of the purple star. You also want to estimate what the partial f, partial of q with respect to x approximately this one. Because then we put all these things together into something that more or less confirms Green's theorem.